Hey everyone. I'm Gilad Bakas. Probably haven't heard of me before. I've been in doing reverse engineering and security stuff for over 14 years now. Originally from Israel, moved to Australia like 5 years ago, and I'm based on the Sunshine Coast in Queensland. And yeah, the Ruxcon guys really wanted to have a kernel talk, so Chris asked me to do this one, and I'm happy to be here. Let's begin. So what we're going to have today, there's going to be two parts of the presentation. We'll start with the general stuff, why go kernel, what's the difference between user and kernel, and then I'll talk to you a little bit about how you go about vulnerability research, what do you do, how do you think, stuff like that, which is not really kernel specific. It kind of can be used for anything, even for most of the reverse engineering projects, and not only for when you're searching for exploits. So that's going to be a fairly high-level part. And then I'm going to move to the very low-level tips and tricks, techniques, what to do. Very low level, and then so I might lose a few of the there, hopefully not. And yeah, we'll go through a few samples. One very simple kernel bug that I used to demonstrate kind of very basic concept, and another exploit thanks to my friend. Some of you may have heard of him, Gilad Bakas. He's the guy who writes DStorm. That exploit was silently closed by Microsoft. That's more like what you'd find kind of in the field today, more realistic. We'll go through that. And at the end, we'll talk a bit about the future of Windows 8 and what Microsoft and others are doing to better protect the kernel. So, why kernel? For years and years, the kernel had a reputation of being much harder than user mode. I always found it to be a bit kind of too exaggerated. I've met tons of researchers that for years done amazing things in user mode, but oh, kernel, nah, I don't do that, that's scary. But with the recent years, we've had lots of development in terms of protecting the user mode. DEP, ASLR, UAC, there's all the heap stuff, and the user mode is become much more complicated to exploit. There's lots of protections there. We've got low integrity mode, or what's known in IE as protected mode, and the sandboxes in Chrome. All makes exploiting in user space very complicated. So we're kind of getting to the point where it's actually maybe easier to exploit the kernel. And at the same time, we saw a lot of code basically moving from user to kernel, and just new technologies. We had a few talks here about WebGL and 3D technologies, and this is just one example of new interfaces that basically allow you to go directly from a web browser to the graphics driver, and sometimes to the actual GPU hardware. And there's many other examples of stuff that was added. So the attack space in the kernel is increasing all the time, and is much bigger than what it used to be back in the day. Another thing that we see happening in 64-bit systems is the introduction of driver signing. So when many attackers, basically, the good example is rootkits. If they want to hide the stuff, they want to be in a kernel anyway. There's no way to do it legitimately because their code is not signed. So basically, they have to find an exploit. That's the only way to get there. And yeah, and it's kind of the same. Many times they need to be in the kernel to do what they want to do, whatever that backdoor hiding. Maybe they want to do some stuff with the network. They need to be in the kernel anyway. So jumping straight can be a really good option. Just while I was working on this presentation, looking and kind of reading about Dooku, I came across this article by Greg Kaiser, basically saying that Microsoft has been extremely busy patching pieces of Windows kernel this year. So far, 56 exploits only this year. So we can definitely see a shift in the market. More and more researchers are moving into the kernel, and we definitely see it in the amount of bugs that Microsoft are fixing. So what's different when you're looking into the kernel? The main thing, and probably most are very aware of, in the kernel, if something goes wrong, that's really, really wrong. You're talking blue screen and a reboot, sometimes a freeze. It's not like in User when you have, Firefox has shut down and everything is nice and you get a nice message, or sometimes you don't even get that because there's exception handler that does all the work for you. In the kernel, every tiny thing that you do or you do wrong, you get a blue screen. The good thing, don't have to worry about permissions. You can do whatever you want, which is very nice. You do have to master a lot more knowledge. You have to have a much wider experience and knowledge of the different parts of the operating system. We'll go over that a bit more later. And something for people coming from user mode, they're very used to the concept of a process. I'm running in a browser now. Whatever the printer spooling is doing at the moment is not really of my concern. In the kernel, everything is your concern, which goes both ways. Like, it allows you a lot more room to play with, but also you can mess with a lot of things, and many times you're not even aware that what you're doing can affect other parts of the system. So just to scare some people away, the stuff that you need to know before you even kind of go and start messing with the kernel. Of course, you need to know all the kernel APIs, DDK, IFS, and very good knowledge of the memory layout of Windows. All these terms, interrupts, IQL, DPCs, IRP, if you don't know what that means, probably shouldn't go writing code yet, and go do some study, come back later. Synchronization, kind of similar to what's going on in user mode, except you're much more likely to cause real mess if you don't know what you're doing. Paging, the actual architecture of x86 or i64, whatever you're working on, the processor architecture. And it's really good to know how device drivers are built, how you communicate with them, yoctals and all that kind of stuff. Oh, wow. Lots of brave people here today. So let's go on. So now I'm going to take a bit of a detour and talk about kind of vulnerability research in general, and from my experience, how you should go about when you come and say, okay, I want to find a vulnerability in a product or a system or whatever. So I always think it's best to first take a kind of a very high look, what the system is, how it works, what it tries to achieve, where are the complex parts. Complex can be parsing, can be virtual machines. There's always issues We're all humans. We have always have problems communicating. Whenever you know, and it doesn't matter how you know it, that we're different teams of developers working on something, the links between the different parts of the code are always good places to look for bugs. In general, when privilege escalation are naturally much easier on the kernel than if you want to do remote exploits. And funny enough, like when I first started with the kernel, nobody was really interested in privilege escalations because Windows, you were running administrator anyway. But the recent years, because of UEC and the shift towards forcing users not to run in under administrator account, we see a rise in the amount of people looking for privilege escalations and researchers working on it, and etc. So that's one thing to There weren't many widespread kernel exploits, like remote kernel exploits, but they are out there. One thing that I personally, people tend to forget, is that many small bugs can form one big bug, and many times researchers kind of overlook, that's a bit unusual, but there's nothing you can do with it. When you research, you really want to kind of write down all the things that you found, even if you can't see how they can be used. Anything that seems to be working not the way the designers wanted it to work, you want to take that into consideration, and maybe you can use that later for something else. I know very broadly 3 approaches for people when they go to research for bugs. There's the high level. It basically says, okay, let's understand how the system works from a kind of high-level perspective, and only then try and kind of figure out where the holes are. There's the low level, which kind of, this looks complex. Let's reverse the hell out of it and then go from there. And the last one is kind of black box brute force fuzzing. But yeah, let's make this motherfucker crash and then go from there. I'm definitely number 1. I think that you can say that every researcher on the planet would have like a main way, which is one of these ways. I think the best way is of course, there's no better way or worse way. You kind of try to always kind of mix these 3 approaches. But yeah, it's funny to see how like different people kind of do things differently. So let's go over the differences between these approaches. So first, the high level. The most important thing before you even begin is to do proper research. It's amazing what you can find on the internet nowadays, and I think like 90% of the work that I do really begins in that research. You can find even like press releases. The companies say, we're cooperating with this company to use their their library, their code, their product. You now know for sure that they're using a product, they're using a library. You don't have to go to the code and figure out what they're using because the knowledge is there. Users are reporting bugs. They're putting dumps, like memory dumps, crash dumps, on the internet for bugs that very possibly could be exploitable. Lots of white papers, everything really, and people don't do it. Like, you really have to know your stuff, investigate, and basically find out what the system you're attacking or you want to attack is trying to achieve and how is it doing it. Then you go, okay, so this is what it's doing. If I was the developer working on this? How would I do it? And again, you go and you research all the different ways that this specific functionality can be achieved. And once you've done that, it's very easy to say, okay, they need to write a file. To write a file, you can call create file. You can do this, you can do that. It's very easy. You have a list of functions, a list of libraries, whatever, things that are very easy to find in the code. So you just go and you just search in the code, and by doing that, you get a very good idea, a high-level idea. Okay, this product, whatever, this system does this. It does this with this API and not the other API. It does this in this order and not the other order. And so you kind of got a really good feel of, okay, what's going on without needing to reverse anything really at this stage. And then you can say, okay, so this is what it's doing. Where would be a good place to look for bugs? What kind of bugs am I looking for? You can say, okay, if I can find something here, then I can probably do that. But you all have to come from high-level understanding of how everything works, and you go on from there. With low level, you do things a bit differently. Which is basically you look for complex code. Complex can be many things. But yeah, just going over reversing, and like you learn how to identify, again, parsing, virtual machines, we said. Anything like in crypto stuff can be very complex sometimes. Anything that communicates, again, interfaces, all places that are good to look for. And then basically what you do is you say, okay, that function looks very complex. I'll go and I'll completely reverse it and look for bugs. And then you go upwards from there, looking to see if you can generate an input or a flow that will get you to the bug that you found. I personally always find it a bit annoying. Like I have all these friends that kind of, this looks really complex, and then I sit on it for 2 hours. Whoa, man, I found this crazy integer overflow. You won't believe it. And then like half an hour later, oh shit, like four functions up the stack. They don't even allow the range of input to come. And then like, oh shit, and go the next one. Which is why I always tend to go from the high level down and not the other way. But having said that, I think that most of the bugs that are found and are published, probably people are doing that. They're saying, oh, let's just reverse. They take a bunch of sometimes large chunks of code. They completely reverse them, and then they say, okay, there's an integer overflow, there's a logical bug, and this is how they work. There's not many people that do the more high-level stuff. The nice thing when you work from high level is that you're more likely to find logical bugs rather than kind of binary bugs. And the advantage of that is that logical bugs are much harder to find and many times much harder to fix. Okay, so the last approach is the kind of black box fuzzing, which is I'm sure many people here are familiar with. You basically want to find all the possible inputs that a piece of code can accept and try all of them. You have to do it in a smart way, because input can have checksums and CRCs and can have to be in a certain structure or a certain length. So you have to do it smartly. You can do it manually. You can do it with a script or a program that you write, or you can use many fuzzing products that are out there. It's a very good way, always worth trying, and many, many times you find really cool things. that's definitely something should be done. And yeah, you basically want to try as many code flows as possible to reach every possible scenario that can result in a bug. Okay, so what type of bugs can we find in the kernel? So the first ones, very much like user mode, are buffer overflows. Stack is exactly the same as user mode. Kernel, the heap of the kernel is the pool. We've got basically, say, 3 types of pools, but 2 for the purpose here, which is one is the page and the non-page. There's very similar things that you can do, and how the pools were like. It's very similar to the heap, is what I'm trying to say. Except that it's a bit with the heap, we've seen again lot more protection that were incorporated into the heaps in user mode, and some of these protections haven't made it yet to kernel. It's a process that's happening, but we're not quite there yet. A very, very popular type of problem that we see in the kernel is null dereference, mostly with privilege escalations. It all comes down from the fact that on a Windows system, you can allocate page 0. And what that means is that if you somehow make the program use an uninitialized variable that had an initial value of 0, either like calling it as a function pointer or using it as a pointer to a structure that has some interesting stuff in it, then you can do interesting things. And another very common bug is input validation. And we'll see, I'll show you examples of these two, of the null dereference and the faulty input later. But these are kind of the things that you mostly see. Stuff that you see less, use after free. I'll talk about an example of that, but yeah, we have that similar stuff in user mode. Direct calling to user code. Not very common, but sometimes drivers do that, or sometimes you can make the kernel do that. It's just simply call user code directly. And of course, logical bugs. Much harder in the kernel, but they are there. Okay, so kind of moving on to the next more lower level part of the presentation. We talk about, you found a bug, what happens next? You want to develop an exploit. As we mentioned before, you really want to know as much as you possibly can in terms of technical knowledge. What I found is that any knowledge you have, you're probably going to end up using it. So you're in the kernel, the entire system is your playground. You know, if you've had a project with whatever, something to do with graphics, DirectX, something, you know how, like, very well how that part of the system works. Then you find an exploit. You're very much likely to use some of the knowledge from that area, even though it can be completely unrelated to what you're actually trying to attack. So it's a never-ending game. You want to kind of constantly learn about new components of the system, new drivers that come in, and keep track of as much knowledge as you can about the operating system and how it works. Creativity, like, you know, always said, it's thinking out of the box. There's always, I've heard the argument many times of whether it's possible to actually teach someone how to find vulnerabilities. My take is that not really. It's a way of thinking that you either have or you don't. You can work on it and improve it. But I don't think I've seen any case of like someone that wasn't anywhere near that way of thinking and managed to do it in a good way. You'll also find that kind of researchers have that same way of thinking in their life, always looking for the backdoor, always looking to see things, to do things like awkwardly. I can definitely see it on myself. So yeah, it's all about creativity. It's a way of art and combining different things to achieve a goal. And again, the playground is a lot bigger than in user mode. You have the entire system to play with. Okay, so this is just one example of a bug that I was working on. I can't disclose the name of the product, but it was a remote execution, use after free. And just to demonstrate the length of the playground and what you do with kernel bugs. So the bug was itself was quite simple. There was an object that was freed, but it was kept in a linked list of objects that are still being used. So what you want to do in that case is you want to get some new code, like that you control, into that buffer that was freed, and you have to do it before someone else takes that buffer, which is the key point. So what we ended up doing in that case is that we found one completely unrelated bug in another driver that we could use to cause CPU starvation, and that really helps preventing others from taking that same buffer. We found another piece of code in another driver that, with some functionality there, we could allocate a buffer in any size that we wanted and copy our data into it. And finally, we activated the vulnerability or the branch of the code in the actual driver that we were attacking to actually make use of that new buffer and execute our code. So that's just to give an idea of the diversity. Like you're working on one thing, but you're actually using other completely unrelated parts to get what you want. This is another example. It's not actually a kernel exploit, but I think it's a really good example of what happens when different teams work on a project, and especially when the user team has no idea about how the kernel works. So I'll go to the next one. It was a DRM system for one of the leading companies in the world in securing of video content. They were more into satellite and cable TV stuff, and they were thinking to move into IPTV, broadcasting over the internet, stuff like that. They've spent, I think, a team of really good developers spent a few good months working on the system. The idea was to make every movie, or the protection of every movie, different enough from the other movie that it would take the same amount of time, which would be a long time, to break the protection of each individual movie, so that it would be kind of not worth your while. So they built this whole compiler that generates movies that, like the decryption code is actually embedded in the movie. All sophisticated, generates different stuff for different movies. But when you come down to the bottom of it, the way DRM works is it basically has to attach a license to your machine. Your machine, it differentiates between machines by whatever, reading your BIOS, getting your MAC address, all these things. To do these things, you need more permissions than you have in user mode. So what they've done is that they created a tiny little driver. So the movie would call into the driver, and the driver would call straight back into user to the code that was embedded in the movie. And that code would then read the BIOS, do all the nasty stuff. And this is how they solved. It's a major security risk because that means that they just introduced a privilege escalation to the system that anyone can use, but we'll ignore that for now because that's not what I want to talk about. So they came to me after like months of work, just basically as they were ready to ship this thing. And I spent 4 days, I think, and I came up with this solution. I hooked device I/O control. Instead of calling the driver, I call straight back into the user code, just putting it in a nice try-catch statement. Anytime that the driver, that code tries to do something nasty, like reading the BIOS, it would raise an exception because it's a privileged instruction. I handle the exception. Instead of reading the BIOS, I read it from a file that I saved before. Whatever Mac, whatever it tries to do, I give it the data from the initial license that I had, from the computer where I had the initial license. And the system is all, they tricked. It always thinks that it's running on the same machine, and I can now use the same license on any machine on the planet. So this is just a really good example of, they put all this effort and this stupid interface just because they had no idea, oh, these kernel people we don't know. So it all comes down to something so simple and like all the effort was basically, I think eventually they dumped this project and decided that they don't want to go into PCs. And to this day, I don't think they've done it. But yeah, it's that can be avoided when you kind of get your user or developers more aware of the kernel stuff and what can and can't be done. And with the eyes of the researcher, when you have such interfaces between a user mode and a driver, that's where you want to look for stuff. Most times you can assume that the user people know less what they're doing than the kernel people. And yeah, naturally there's room for stuff. Okay, so down to the hardcore part of the presentation. Different tips and tricks to do stuff when you actually have an exploit. Many times you have an ability to write some arbitrary data to any address that you want. So good places to override. Callback function pointers. There's many examples in the kernel. The kernel is full of callbacks. One of my favorite ones is page fault notify routine. Basically almost every access violation that you raise will result in a call to that callback function. So if you can override that before the access violation, you're in business. Data segment variables are constant between natural to the relative to the base address of the model. That means that they'll be constant for a specific build of the operating system. So if you know the build of the operating system, you can guess them, or not guess, you just know them. GDT and LDT tables, there's a really good paper about that by Juru. I won't get into too much details, but basically, even with 1 byte arbitrary write, you can manipulate a call gate and get code execution by writing to the LDT and GDT tables. This dispatch table is the method that was the most popular until recently, until Vista, when they blocked it. Dispatch table, for those of you who don't know, is the table that the native API uses to go from user to the kernel. So when you call whatever anti-create file, it translates to a function code, and then using sysenter, it goes into the kernel. The kernel finds the code for the function, and gets the equivalent function in the kernel. So that would be ZW create file. That table on XP is writable for the kernel. So it's very easy to just override that function. Then when you call anti-create file, it calls your function instead of create file. But that was blocked on Vista. They just put page protection, it's read-only, so you can't write there anymore. Other non-fixed addresses, which is more relevant to privilege escalations. If you can run code, there's a new technique that, again, Gilad Bakas and Tarjei Mendit, I hope I pronounced his name right. They've done some really good work on Win32k, and one of the things that they found is that the window handle table is actually mapped to user mode. It's a shared section. In that table, there are kernel pointers to the window object, and in that object, there's, among other things, a pointer to the window procedure. So what you can do if you're running code, you can access that table, you can get a pointer to the kernel window procedure that's relevant for special kinds of windows that are processed in the kernel, like menus and tooltips. So they have their window procedure is, or a part of it at least, is in the kernel. You overwrite that pointer. You can then send a message to the window, and you get your code executed. It's a very nice technique. There's other examples of kernel pointers that are passed either by design or by mistake to user mode that you can use to find stuff that you can overwrite. Another good example that Jeru found is that some of the Win32k syscalls are actually defined as void or ushort, and that they leak part of the, I think it was ethread in the return value. So you get the kernel pointer to the ethread, and from there's many things you can overwrite to get code execution. So these are all things that you can do if you're already running on the machine under a privileged user or something like that. I mentioned a tiny bit of that before. It's a very nice trick, similar to SEH stuff on user mode. Many times, what you have, you can. A good example is a linked list. You overwrite one pointer, so you get arbitrary write, and then immediately straight afterwards an access violation. Blue screen, you think, oh, blue screen, I'm fucked. You're not. If you can write first, then there's lots of stuff that is happening after an access violation that you can use. In one incident we managed, it was extremely funny. We actually managed to run code after the blue screen was already displayed. So that was very amusing. We couldn't stop laughing for a while. That was blue screen and WinDebug with our in3. So what I'm trying to say is even if you get a blue screen, unless it was a direct call to KE bug check, there's a chance that there's still things you can do. You can come out of an access violation and restore the context of the system and continue to run. It's all possible. It can be a bit tricky, but can be done. Another problem that many kernel exploits developers run into is that they're trying to call anti-query system information from a 32-bit process running on a 64-bit system. All the pointers that are returned are truncated to 32-bit by the thunking system. There's a nice paper about it, thanks to Mark Dowd. I don't know if he's here. He sent me that link. What you can do is you can use the built-in call gate that the thunking system uses to temporarily switch to 64-bit. do the call to query system information from 64, get your data, and go back, return to 32. So this is a way around that limitation. And another tiny bit of information. The 64 TEB in a WOW64 system can still be accessed without doing all this mess. It's mapped to GS0 instead of FS. Another main problem that exploit developers have in the kernel is quite counterintuitive. You think, oh, you're in the kernel, you can do everything. But many times what you want to do is you want to run user code. And that's actually very complicated. Because again, you're in kernel, the kernel doesn't launch processes naturally. There's no API for that. So let's look on a few ways that this can be achieved. The first and most common technique that people use is to change the process token, which is basically very simple code. You find the token for a system process and change it in the, I think it's in the K process, and you got your process, whatever process that you're running in, a system token. Of course, it's all nice and easy code. It can be, I can't remember how many bytes, but can fit it in a very small shellcode. It works pretty well. It's reliable. The problem is then that the user mode then has to do all the nasty stuff. Let's say if you want to actually inject code to a system process, the user code then has to call whatever, create remote thread, write process memory, and many security packages can actually detect that code, so it's a lot more noisy. So that's the main problem with that. Another method that is kind of gaining popularity now is user mode APCs. APCs, asynchronous procedure calls, are a way for the system they call it alert user thread. So basically, a user thread can say, I'm going to sleep, but if something really important happens, wake me up. To do that, you have to call one of the wait functions, so sleep, wait for single object, this function, the X alternative, and you specify there's a flag called alertable. If you specify it as true, then you mark the thread as being able to receive those user mode APCs. So what you can do is you can issue an APC to a thread in the process where you want to inject your code, which is nice because it gets you into whatever a system process or exactly where you want to get. And you can theoretically inject to any process in the system. The problem is the thread has to be in alertable state already. And not all, most threads aren't. In most system processes, you can find threads that are, but not always. So it really depends what you're trying to do. Another option is to actually force the alertable state on a thread. The problem with that is that it's bloody dangerous. You have a thread that just is waiting for an object, for instance. It's not expecting to get woken, and basically what it does when you force that flag is that it wakes that state, and that wait function returns before the wait event actually happened. So it's quite easy to put the system in an unstable state. But again, it depends what you're trying to do. Many times you can just find a thread that is alertable and you don't have to worry about all the stuff. A nice trick that I forgot to put here, the alertable flag is the offset. It changes the offset in the K thread to the alertable flag changes all the time, and it's quite difficult to find it. You have to write code that is specific to a build. that can be worked around by issuing a kernel mode APC. The kernel mode APC always happens even if the thread is not in alertable mode. Once you're in the context of the kernel mode thread, you call a wait function, and you give it an alertable flag of true, and then you don't have to, basically what it does is to set that flag. You don't have to know the offset, you don't have to mess with the k-thread yourself, and you reach the same functionality. That's a pretty neat trick. Next, thread hijacking. Theoretically, you can pick any thread in the process where you want to inject into, change the context, change the AP, run your code. Again, it's very nice because it gets you wherever you want to whatever process that you want to get. The problem is sometimes it can be very difficult. It can be very difficult to restore the context. All right, I'm running out of time, so I'll go quickly. Another theoretical way is to create a new thread. The problem thread has to be registered with CSRSS to be functional. Very complicated, can be done, and that gives theoretically the perfect solution. You're just creating a new user thread in a process from the kernel. The last one that I'll talk about is API hooking. If you know that there's an API in user mode that is going to be called, you simply hook that API in user mode from the kernel. You change the memory. Next time the user mode application calls the API, your code's going to get called in that context. Let's quickly go over an exploit in AFD. So can anyone spot the problem? I'll give you a hint. Probe for write basically raises an exception if the memory is not writable, but if it gets 0, it never raises the exception, so it's all good. No one? The problem is that they use different, there's two problems. One, the main one is that they use a different length for the probe for write and for the actual copy. So if you, the user mode supplies a length of 0, what happens is the probe for write, again, 0, nothing happens, all good. It goes to the copy, and the copy then copies the remote address to any address that you like. So you can basically overwrite any address on the system. So any address on the system, but you don't really control that data. That data is the remote address. It has to be a connection that is alive, TCP connection that is alive. What do? It looks like that. So O2, port, and IP. You can't really control it. Basically, your options, you can override a flag somewhere, and hopefully that will allow you to do stuff that you're not meant to do. Or maybe you don't even need to control the data. So let's see. If we connect to 127.0.0.1 localhost, that's 7F.0.0.1. Port 445, open on any Windows machine, that's SMB. That gives us something like that. We want to get a 32-bit pointer that we can overwrite to an address that we can actually control. So we've got BD7F with Little Indian. That gives us 7FBD. That's user mode, perfect. We can put our code in there. So we can overwrite any address with this address that we can control. This is an old bug just for the example, so we can use dispatch table. So basically what we're doing, we allocate page 7FB0. We find the address of a function in the dispatch table. The one that everyone's using is query interval pointer because it never ever gets called. We call device IO control to do the override, and then we call the function. I'll give you a quick demo of that code. So I'm guest running the exploit. System. All nice. This is an exploit that was closed by Microsoft a few years back, and they use it to demonstrate what not to do in drivers. I don't know if I have time for that. Probably. All right, we'll do it quickly. So 5 minutes. I'll do it 3 minutes in that, and then I'll leave time for some questions. So as I said, this is an exploit that was found by a friend of mine, and it was fixed silently by Microsoft. It's a bit more complex. It relies on a feature of Windows. When you create a window or a window class in Windows, you can ask the operating system to store a few extra bytes with the Windows structure in the kernel for you. Some special windows like menus and tooltips use that extra bytes that can be stored to store private data. They do it in the kernel, so it's all kernel stuff that's stored in those private bytes. To change the extra bytes of a window, you use the API set window long pointer. Naturally, when you're trying to change private bytes of a kernel window, it doesn't allow you to do it. But how does it know if you're trying to access private bytes or not? There's a table that basically the table has the window type and the amount of bytes that are allocated for the window object plus the private data. This table is initialized with the right values. So for the, let's say, a menu, it would have just the size of the window structure plus 4 bytes of private data. There's the bug by calling an undocumented, unexported function called whatever register class xwow. You can actually change data on that table. And so you register a class, you give it a negative extra bytes number. And what you've done is that you've just destroyed the value in the table. So the next time that you call set window long pointer, the check fails, and it allows you to change. So you give it index 0, you change the 4 private bytes, and that allows you to change data that is you're not meant to be touching. And then what you have to do is, again, you have to find a window that has some interesting stuff in those bytes. The menu window happens to have a pointer to a structure. When the window is destroyed, a value in that structure is nulled. I'll skip that. It's not very interesting. So basically, you can write null to, again, any address that you like. And you can allocate stuff at null. You can just copy your code into there. You're all done. I think we'll... So just quickly mention the feature. We just null dereference Windows 8. You can no longer allocate the first 64 bytes, 64Ks of memory. That's probably will block most of these null dereference bugs. As we've said, they're slowly catching up on all the stuff that they've added to the heap allocation in user mode. They're moving it to the kernel. And there's, more stuff added to prevent dangling pointers with linked list and stuff like that. So there's definitely work that's being done by Microsoft to make things nicer. I'm running out of time. Just any questions?
Anyone got questions for Gilad?
I do have source for the exploit. Yeah, I just have to find out whether I'm allowed to send it.
Hey, Gilad. Do you think that the 64K null-byte dereference protection in Windows 8 would actually stop you from exploiting that last bug?
Yeah, this particular one, yeah.
Couldn't you just do like a partial overwrite of some function pointer, and then you'd be calling into userland but offset past 64K?
No, because you only have like, I don't think, maybe.
Yes, it depends on alignment or something. But.
Yeah, it will depend on alignment, but yeah, maybe. Not sure.
Thanks.
Anyone else? All right, ladies and gentlemen, Gilad Bakas.
Thank you very much.